Okay, so let's start our lecture today. Uh, yeah. So I will change to a new place. So yeah. Um, yeah, but I will try to continue with the with yeah. I think last time I finished the let me think. Uh, yeah. So let me see. Uh, so yeah. So yeah. I think last time we just showed the convergence of the y stress p function, right? So we showed that basically using the property that if a sequence of holomorphic functions converges locally uniformly to a limit function, then the derivative will also converge locally uniformly to the derivative of the limit function. Yeah. So we use that property to show the property that the convergence of the y just theta function will gives us the convergence of the p function. Yes. So yeah. So that's the result that we showed last time. So and here I think we can just pick up from the place where we started, right? So because I think we start the business of showing the all the convergence criteria. It starts from the property that. So here we are aiming to show. We are aiming to show that the periodicity of the Zeta function is equal to zeta of z. Okay, so from plus eta 1. And then we also have the property that zeta of z plus omega 2 is equal to zeta z plus omega plus eta 2. Okay. So we're so this eta 1 and the eta 2 are just some constant number, right? So it's in constant number. Okay, so let's just show this one. So we know by definition that this zeta is exactly. So let me write out the zeta. So zeta z is equal to sorry, let me just use this one. So zeta z is equal to 1 over z. Oops. I think just some water on this one. So 1 over z plus. Oops. Wait. Shoot. It get wet. Okay. So plus. Oh shoot. Summation omega not equal to 0 of 1 over wait, is this being recorded? Okay, good. Yeah, so it should be 1 over z, right? So 1 over z plus 1 over z minus omega plus 1 over omega plus z over omega squared. Okay, so here, sorry, there's some wet space, so cannot really write it down because it's wet. So so 1 over z plus, so this is the summation sign. Okay, good. So this is 1 over z minus omega. So can I see? Is this clear? Okay. Okay. Yeah, so this is 1 over z. Shoot. Yeah, so 1 over z. Okay, so so we have the zeta of z plus omega 1, right? So let's write out what that is equal to, so here we have 1 over z plus omega 1 plus plus summation of omega not equal to 0 of okay, so that should be the same thing, right? Wait, not exactly. Yes, so wait, so 1 over z plus omega 1 minus omega plus 1 over omega plus z plus omega 1 over omega squared. So let me think. So yeah, so I'm thinking of that because yeah, so because I'm thinking of if we just look at these two numbers by itself, right? So we have the property that because okay, so hold on 1 second. So yeah, so definitely the convergence is not a problem in this case, right? So because for this sequence, I think we use the property that yeah. So we show that the convergence of zeta z, right, for on any compact subset, right? So of a C minus that is point. So there should be no issue of convergence of this one, right? So convergence, there is no problem. Yeah, of course there is no problem, and also so here, right? So basically these are just two numbers, right? So this is a complex number, this is a complex number. So and then we take the difference between these two numbers. So we will get a number, right? So this is true, right? So we know that okay, so we know that yeah, so maybe just say that. So let's say let's just say that maybe let's just first fix one z naught. Okay, so fix like a z naught in this c minus the lattice point. Okay, so and then we have that. So just replace every z with z naught. Okay, and then let eta 1 to be equal to the difference, right? Shoot. Yeah, I want to be a little bit careful here, but sorry, I think I should go in the other way. So I think I should go. Maybe I should start with this one, right? Because on the book it's being defined this way. So maybe I should start with the z naught plus omega 1, and then minus zeta of z naught by itself. Right. So it's well defined. Okay. So this is well defined. And then so what we're gonna do next? So what I do next is that, so basically what I want to do is that you want to show that because this is just true for one point, right? So I define this eta 1 to be just the difference for this specific point. So but this argument requires this to hold for any z, right? Because this is a statement that holds for this zeta function. So basically it must be true for any z, right? So basically what I do is that I want to show that so if I show that their difference after taking the derivative give you 0, then I'm done, right? So I want to show that these derivatives, the ddz of z plus omega 1. Oh, sorry. ddz of the ddz of zeta of z plus omega 1 minus zeta of just z, right? It's equal to 0. Okay. Okay, so why that's equal to 0? So so let's just expand all the expression here, right? So let me just expand them out. So we have zeta of z plus omega 1 minus zeta of z. So this is equal to here that's just so this is 1 over z plus omega 1, and then plus the sum here. Yeah, so I want to be a little bit careful about the limit here. Minus. Can you guys see that? I think my letter is a little bit small. But okay, maybe I'll keep it larger. Yeah, but for now I think maybe it's fine. Yeah, I think it's fine for now. So yeah, I'll keep it bigger. So plus 1 over omega, and then plus, sorry, so this should not be z naught, right? So I'm using letter z for any z. And then plus, it should be z plus omega 1 over omega squared. Okay. So this is the limit of the partial sums term. Okay. And then minus. So here we have 1 over z. And then minus the sum, minus the partial sum of this guy. 1 over, so this is just z minus omega plus 1 over omega plus, so this is just z over omega squared. Okay. Okay, so now, so definitely there is no issue between this point and this point, right? So so let's see. So oh, excuse me. So here, right? So yeah. So let me just do like a common denominator here. So here I get z times z plus omega 1, right? And then so this is the denominator, and then for the numerator, so I have z. So this is z, right? So and then this is z plus omega 1. So it should be z minus z plus omega 1. Okay. So this is like just these two terms being combined together. And then, so yeah, I think the main problem maybe comes from the sum term, right? So here, so this one is a limit, right? So this guy, so this number is a limit of some partial sums, right? And this one is also a limit of some partial sums. So do we have a property? I think we have the property that if I take the limit of n goes to infinity of just some bn minus the limit n goes to infinity of an. So I think it should be equal to the limit of n goes to infinity of bn minus an. I think this is true in general. So let's see. So let's see. So for this bn, right? So let's do that. So so let k, okay. Maybe I'll use letter b, okay, to denote the limit as the limit n going infinity of bn, and then I'll let a to be this limit. Okay. So this is just b minus a, okay. So so for any, let's see, so so for epsilon large, I know that this B is very close to Bn is very close to B, and An is very close to A, right? So and then why is Bn minus An very close to B minus A? I think we can use some triangle inequality stuff, right? So basically, yeah. So what I want to show is that I want to show this. I want to show that this limit is exactly equal to this B minus A, right? So I should write. So basically, what I have is that B minus A. Oh, sorry. Maybe I think I should start with this guy. So I want to show that basically this this is the limit, right? So this is Bn minus An minus this B minus A. So basically I want to show that for this large, this difference is very small. It's less than epsilon. Yeah. So for any epsilon, I can choose large so that this guy is less than epsilon, right? So basically, so what I can do is that so here this is just Bn minus B, right? And then what I have is that maybe I can use a plus. So plus. So this is A minus An, right? Oh, okay. So you see that? So this is less than or equal to the modulus of B minus Bn plus the modulus of A minus An, right? By the triangle inequality. And then, so we know that for this large, this can be very small, right? So choose n such that this is less than epsilon over 2, and then choose n that pick n1 such that this one is less than epsilon over 2, and pick n2 such that this one is less than epsilon over 2, and then pick the n that is the maximum of n1, n2, so that these two will always stay within the epsilon over 2 range, so that these two can be less than epsilon. Okay, so yeah, so this is true in general for just the complex value function, right? So where this A and B